Hi everyone, let's try this lesson again. Thank you to those of you that emailed me and let me know that the video was not working. So hopefully this one will work. Welcome to lesson 531. So if you go to page 67, we will find our warm-up. First we need to conclude whether or not the triangles are in fact similar. So if you look at your three triangles, they do have two sets of congruent corresponding angles, and for that reason I can conclude that all three triangles are similar to each other by AA similarity. Now I have to find three different missing side lengths. That's what they want us to do in part 2 of the problem. So is it possible to do so? Yes, and here is my work. So just want to kind of reiterate, you might set up your proportion a little differently than I do and still get the same answer, and that is basically because we are being consistent. So here is my setup for how I found side length y, but I just want to mention, someone else might have done y over 5 is equal to 3.5 over 2, and you would get the same answer of 8 7/75 of a centimeter. Take a look at how I solved for x. And again, I did two different setups for how to go about finding side length z, and both setups will give me the same answer of 3.5 centimeters. I'm just going to kind of quickly scroll through the previous day's assignment. You could kind of see the work and setup that I've done. Hopefully that'll help you out in case you had any questions. Friendly reminder, the nice thing about having this being videotaped is if I'm going too fast, please feel free to pause the video or rewind and re-listen to it. Real quickly, if you take a look at example 5, here's my proportion, here's my setup. I'm putting parentheses around the x plus 2 and 7 minus x, just to kind of remind you guys, distribute that 3.5, distribute that 7, and then hopefully you got x to be 4. Also, once you are solving, are you setting up similarity statements? Are you stating triangle ADE is similar to triangle CDB? Remember, this is not just one way of naming these triangles. Maybe you might want to say triangle AED. Then you would say that is similar to triangle CBD. One thing I want to point out with example 8, notice most of the information given to us is in feet, but then Sheila's height is in feet and inches. So 5 feet and 6 inches is really just 5.5 feet. So that's where I got that value from. So all of my numbers here in this particular proportion are in feet. So keep in mind, sometimes with measurement, you might have to convert your units. Both of these are acceptable answers. All right. So hopefully by the end of this video, you guys will continue to determine if triangles are similar. I'm going to teach you 2 new similarity statements. And once we know triangles are similar, we can continue solving for x, which typically is a side length for given triangles. All right, so if you need to or would like to go to page 68, you could jot down some notes. So one similarity statement that we know already is AA similarity. I basically need 2 sets of corresponding angles to be congruent. So if I have the following, I can say the triangles are similar by AA similarity. Here's one of our new similarity statements, side, side, side similarity. Basically, all three corresponding sides need to be proportional, meaning they all have the same scale factor. And then our last similarity statement for today is going to be side angle side similarity. And basically, what I need is two sides to be proportional, and the included angle or the angle between those two sides need to be congruent to each other. If I can show this, then I can say triangle ABC is similar to triangle XYZ. All right, so if you turn to page 69, this will take us to our first example. We need to prove if the two triangles are similar. So one thing I want to point out, if you look at my markings, I right away marked angle 1 and 2 to be congruent to each other because they are congruent by vertical angles. All vertical angles are congruent to one another. Also, this is something a little different. Look at how I marked my triangles. So focusing on triangle ABC, I called side AB small because it's the shortest side. I called side BC M for medium because it's my second smallest side. And then I called side AC, I labeled it with an L for my longest or largest side. And I did that for triangle CDE as well, just so that when I want to set up proportions to find the scale factor, I have kind of a nice little reference now. And that's what I'm trying to show you down here. So I compared 8/12 with 6/9, and notice that reduces to 2/3, and then I did 4/6, and that too is 2/3. You could have given me the decimal of 0.6 repeating as well. But basically, this is showing me that the side lengths are proportional. Therefore, my conclusion is triangle ABC is in fact similar to triangle DEC by side angle side similarity. Or I could even show that these triangles are similar by side similarity because of all the information they gave us. You do not have to prove it both ways. Pick one. Both of them work. All right, page 70 takes us to the rest of our examples. So in example 2, we want to determine if the triangles are similar. So look at what they gave us. They only gave us one set of congruent angles. For that reason, I cannot use AA similarity to justify if the triangles are similar. Likewise, they did not give me all three side lengths, so I cannot use side similarity. So the only method that would work is side angle side similarity. And let's confirm this. Let's confirm whether or not these side lengths are in fact proportional. So again, look at my marking. 6 is smaller than 10.5, so I call this my small side. This is my larger side. 4 is smaller than 7, so I call this my small side. This is my larger side. And that's how I set up my ratio. 6/4 is equal to 10.5/7. These are in fact the same. Okay, this and this gives me the same K value. So therefore the sides are proportional. So side angle side similarity holds true, and that's why my two triangles are similar. However, not the case in example 3. One thing I really notice in triangle ABC is it's an isosceles triangle. Two of the sides are congruent. That is not the case in this larger triangle. So in all honesty, I can quickly disprove that the triangles are not going to be similar. Triangle ABC is isosceles, triangle DEF is not isosceles. There's no way all three sets of corresponding sides are going to be proportional or have the same scale factor. Alrighty, lastly, example 4. So one thing I want to point out is notice how the triangles are highlighted, okay? So side AE is really these two segments added together, hence the 4.5, okay? For this larger purple triangle, side FD is really x plus 2.5. And I kind of use that to guide the way I set up my proportion. So just to kind of organize the information, side DF is x plus 2.5, and that corresponds with side AE on the smaller triangle, which is 4.5. And then if I go back to the larger triangle, DC is 6, and BA, its corresponding side is 3. And you can see how that relates to my proportion right here. Okay. So I go about it as kind of setting it up when I cross multiply. You can of course distribute the 3, distribute the 6 and solve for x, but just a little shortcut or trick. Maybe let's say you don't want to distribute. Okay, let's say you don't want to distribute. What I could do instead is I could divide both sides by 3 first. And if you go over here, that's how I get the 2 times 4.5. And now that's equal to my x plus 5. Sorry, 2.5 plus x. And then 2 times 4.5 is 9. Subtract the 2.5 over, and I've solved for x. I know they don't ask for it, but just to kind of reiterate, x is side length DE, which is 6.5 units. And if I wanted segment DF, it would be 9. It would be the 2.5 plus the 6.5 that I just solved for. All right, let's try to wrap things up. So with the problem-based task, first, it's kind of lengthy. Feel free to kind of read through the problem. One thing I want to notice is Blair's height is in feet and inches, and his distance from the mirror is all in inches. And then the distance of the mirror from the house is 450 inches. So for that reason, I chose to change Blair's height into all inches. So 5 times 5 feet times the 12 inches gives me the 60 plus the additional 10. Add that up, that's how I got 70 inches for Blair's height. Okay, and that's equal to the 450 over 105. Here is the work. So if you basically multiply the 70 and the 450 together and divide by 150, we've isolated the x. That comes out to 300 inches. But we want to ultimately know how many 5-foot sections of the downspout do we need. So because everything is in inches, but the spouts are in feet, I'm going to do 300 divided by 12, and I get 25 feet. And then they sell them in 5-foot sections, so I'm going to take 25 feet divided by 5, and therefore I need to buy 5 sections of the downspout. Okay. So there's our PBT. Again, none of this would have really been possible had these triangles not been similar. But by AA similarity, the triangles are similar, right? Because as a nice little reminder, all right angles are congruent to each other. So these angles were given to us, and we can conclude these right angles are congruent. All right, so here's the assignment that will help you guys kind of better understand the lesson. You can go in your workbook. Here are some notes. Again, this is all in your workbook. Show you some answers real quickly. and I appreciate you guys watching the video.